need a charger?
No.
Oh,
Yeah.
If I go on for so long that we run out of battery.
Okay, so welcome to the last lecture on JavaScript. Today you have this special honor to hear about this from Carolina. Carolina, you have probably met her. She's a teaching mentee in this class. It's a little different than a teaching assistant. Teaching mentees, for one, don't get paid, but they get a grade and they get to teach a couple of lectures. So Carolina will talk to us about layouts, especially pie charts, force-directed layouts, and then later about maps. And then if we have time, we will also do one more design critique. But yeah, let's get started.
Thanks. Hello everyone. For those of you who don't have been to my seminar last Friday, so I'm Carolina. I'm Alex's first year PhD student. I actually got into Viz when I took the same class at Harvard when he taught it a few years ago. And that's when I switched over from oceanography, which is I used to be an oceanographer, to computer science. So this is really kind of stuff that I'm excited about, and I hope I'm able to explain this to you in a way that makes sense, but as always, feel free to interrupt. So we're going to start talking today about layouts. And when Alex stopped his last class, so far we've done a lot of arranging elements with rectangles, circles, all these SVG elements, but we were doing them one by one. There was nothing very fancy about it. Now we're starting, not that pie charts are fancy, but we're going to take this a step further. We're going to start arranging things in ways that are a little bit more elaborate. And for that, we're going to use the D3 layouts, like pie charts and force-directed graphs. Now, in the previous version, version 3, and if you guys go online and look for examples, a lot of the stuff is in version 3, so that's why we bring it up so much. Now we have a flat namespace, like I mentioned in my talk on Friday. So it's all one thing, so you don't really know if it's a layout or if it's not. So it's important to understand the difference between what's creating paths and what is arranging them on the page. And I'm going to hopefully cover that in detail in the pie chart. So we're going to start off with a few slides on D3 layouts. So no good Viz class doesn't talk about pie or donut charts. The only difference between pie and donut charts is that the donut chart has this inner radius. Other than that, they're created the same, everything else is the same. So I'm going to talk about them interchangeably. Okay? There are two functions that we're going to use to create this pie chart. And I'm going to go back to the lecture code where we have that actual, and we're going to play around with it, we're going to create one. But I do want to make it very clear what the difference is between the two that go into creating this pie chart. So we have d3.py, that like I said before was d3.layout.py. So you know that it's the whole point of it is to actually generate the positions on the page, but doesn't actually generate the path. And then we have d3.arc that takes in the output of d3.py and creates the arc. So those are the two functions that we're going to use to create that pie chart. So the d3.py function actually, like I said, it doesn't generate the shape, it gives you the angles for your data to put them on the page. So it pretty much arranges them in the layout, but doesn't draw anything on there. So when you do d3.py, you're not going to get anything. You need to do d3.arc that takes the output of d3.py, and that will actually generate the SVG path that is our donut chart, or the individual wedges that make up that donut chart. So the d3.arc is similar to d3.line that hopefully you guys have been using in homework 2, and other path generators. So when we look at them in the console, you'll see that it's actually the coordinates that draw that shape on the actual page. So let's see how that works with the data. So here we have the line of code you're going to start off with, d3.py, and here's the sample data set. It's actually kind of small. This is what we're going to be using in the lecture in a little bit. So you see that it's just a JSON object, or sorry, just an object that has a name field and a value field. And the value here is shared. Notice that they're both just fields, and D3 doesn't really have a way of knowing which one you want to use as the value, so we're going to tell it which one. But for now, you have these two fields for each data point. And you give that into d3.py, and you create this variable called pydata. And what pydata has are these elements, and it creates these for you. So once you do d3.pydata, it will spit out data, index, value, start angle, end angle, and pad angle. The first two, data and index, are clearly, you can clearly see what they are here. So there's going to be as many pydata elements as there were the data elements that you gave it in here. So for each one, data is this entire element here. So data 1 is going to be this, data 2 is this, data 3. The index is 0, 1, 2, 3, and 4. So you can go back and grab the entire data element if you need to. And then value, start angle, end angle, and pad angle all relate to how it's going to look on the page. So we're going to look at those separately. So this is what that's going to look like eventually, the whole pie chart. So I've told you what data and index are. This is what the arc represents. Now it's important to distinguish arc from angle, right? So this is the value of this arc, and that is stored in the attribute value. Then we have the angles, which the start angle and the end angle and the padding angle. Right now there's no padding. If there were padding, that means that in between each wedge you'd have a little bit of white space. So maybe you want to make those wedges very distinct for an infographic or something that's very clear, you can add that padding angle. So in this example that's set to 0, but the start angle and the end angle. Now remember, this start angle and end angle are calculated by d3.pi. You're not giving it. You gave it the data and it said, okay, I have 360 degrees to work with. I have this many data values, and so for each one, this is where you should start, this is where you should end. And I included here this reference of 0, pi over 2 pi, because that's how I measured it, so the 0 is here. And we'll see in our example that if we change that, if we force the start angle to be, say, pi over 2 or minus pi over 2, that just rotates the entire thing, like one way or the other, so you can control that. But the default starting 0 point is here, and it goes this way. Then we actually feed in that pi data that we just got out of d3.pi into arc, and that will actually generate it. In this case, I actually made the donut so you can see what the outer inner radius attributes do. So here we have the inner radius, oh actually this one's set to 0 in my example, it's not. Yes. So the inner radius is some value and the outer radius. So these are the two attributes that you can set within the arc. Not that you can't set, that you have to set. So when you give d3.arc, you need to give it the output of d3.pi, and you also need to tell it how big you want it to be, and if you want there to be that hole in the middle to make it a donut, and that pretty much creates it. And notice that you also have 3 more options here. Corner radius, and you also have start angle and end angle. So the corner radius is if you wanted to make these rounded, and that is especially useful if you have the padding. So your wedges, and I can put an example here, so think of this as being rounded. It's an aesthetic thing. It just rounds off the top so your wedges are not as sharp. And then you have start and end angle. Now suppose you didn't give it any data. The idea of it having these two attributes is you want to create an arc, and you want it to start at 0, and you want it to end at 180. That's it. You don't care the value, you don't care, you don't want to give it data. So that it gives you the option to say, okay, I'm going to set my start angle to 0, I'm going to set my end angle here, and it's going to create an angle of 45 degrees. Of 9 degrees, sorry. I should take the class that comes before this one. So that's pretty much the syntax of d3.arc. Another very useful function or attribute of the arc that got spit out by d3.arc is arc.centroid. It's great for labeling. And arc.centroid for each data point gives you this little black point. And it's important to notice that this is not actually the geometric center of the arc. It's just the middle of this distance and the middle of this distance for each wedge. And it's usually where people put labels. So whenever you're going to label stuff, you're going to see this when we actually go through the working example, you use arc.centroid as the position of your text labels. Okay? So that's pretty much the syntax and how we create pie charts. So let's actually go through the HTML file for those of you who have this on your computer.
I got a question.
Yeah.
So if the centroid isn't the geometric centroid, how far out is it taking to go?
How far out from?
From the center. Like from the center of the circle out towards the edge of the circle.
Oh, so it's the center in the sense that if you take this distance here, let's suppose we said our outer radius was 100. It's 50.
Okay.
And then it's the center, the distance from this to this arc, it goes in the middle.
Okay.
Okay?
Got it.
Okay, so we're going to go through, the beginning of this code hopefully is very intuitive to you by now. One thing I do want to point out, see how this is commented, I left it comment out instead of deleting it entirely. I was talking to Alex about this, is that for those of you who saw my lecture on the upgrades, version 4 versus version 3, is that you can no longer set multiple attributes at once without actually including specifically D3 selection multi. And then you use .atts with an S or .styles with an S. For the sake of simplicity for our code, we're just going to set them in separate lines. Attribute A equals 4, attribute B equals 3, But if, when you're coding, you do want to set them all at once, I suppose you have a whole list of attributes, then you want to include that, and then in your syntax you use attributes with an S. I did post on Canvas an announcement with my slides from that lecture, from that talk, so you're welcome to go through that where I did talk about that. Okay. So here we have that same data set that I showed you in the slide earlier, right? We have a very simple data set where we have the market share, different operating systems, and the actual value. This example was one that Mike Bostock created, so you can find it online at this URL. So we create height and width variables. We create the radius, which is the radius of our pie chart. So we pretty much just take the width and the height divided by 2. We use the minimum because we want to make sure that it fits inside a box. Because if it's a very tiny box, we want it to still not go bigger than the box. Then we create a color scale from what Alex was talking about before in the last class. Ordinal scales. We have 4 different colors. And then here we're going to create our arc. So notice that right now, our arc doesn't have any value, oh, here it is. Our arc doesn't have any data, right? So we don't have to pass the data in right away. We're creating this arc just like d3.line. You can give it the data later. So we create it called d3.arc. We set the outer radius to the radius we computed before, but a little bit less. It doesn't touch the borders. Our inner radius is 0. If we wanted to make it a donut chart, we would set an inner radius to something like 100, which I believe is what I set it to when I did the screenshot for the slide. Now here we have the pi, d3.pi, and I want to point out what this .value function does. Now last lecture, Alex talked about the accessor function, when you give it a data point and then you tell it which one of those fields you want to extract as your actual value. This is what we're doing here. We're telling it that we want to use the share attribute of our data as the value of our wedge. Okay, so let's suppose you had other things. You had percentage of something, any other number. You can just change that. So you go say, okay, now give me the same pie chart, but instead of plotting the share, plot this other attribute. So it's an accessor function, and you pretty much just tell it which attribute to get from your data object. And then we go ahead and execute it. So this is that same form we saw on the slides, right? We pass our input data into our pi function, and that gives us pi data. And then actually, here, let's look at the console. Ooh, that's very small. So remember in the slides when I said when we apply the data to the pi layout generator, it gives you as many objects as you have data points. So we had 5 data elements, right? 1 for each operating system, and it generates 5 objects. So in the data field, you have the entire element, both the OS field and the share field. Then we have the other attributes that we talked about. We have a start angle, end angle, the index, so this is the first element in that array, the padding angle, which is set to 0, and it calculated 82.8, it didn't calculate that, sorry. The 82.8 is the actual share value. And the end angle is what it calculated here. So for our first element, it's going to start at 0, and it's going to go to an end angle of 5.0, and this was what d3.pi did. It calculated that number for you. It didn't draw anything, it just said this is the number. And then d3.arc is going to take the start and end, and it's going to draw the wedge for you. So that's what pi data does, right? Then we feed that into, so here we're going to feed it into the arc function. We're just going to give that first value, and then we'll see what it looks like. So here's the arc path based on pi data. So this line here is the actual path definition for the wedge defined by the first element in our data. Okay? Great. So that's how those two work together. If you didn't have data, you could create your arc just by telling it specifically where you want it to start and end. And you could create a donut chart just the same, but that's kind of boring. Okay, then we're actually going to do what we've done before with rectangles, but now we're going to create arcs. So we're going to group all of our arc class elements together into a group. We're going to give it the data, the pi data, and we're going to give it the class arc. We're going to make the path. And here, is where we give the actual path. So this description here, this move pen from here to here to here to here, goes into the path attribute, or the D attribute of our path, and then we append a text. And here's where that centroid comes into play. We're actually going to use the labels to label each one of the wedges. So this is a similar syntax to what we were doing with the accessor function for the value. Here we're saying we want our text, for each element D, we want our text to be the d.data.os. Okay? Does anyone know why it says d.data.os and not just d.os? If you kind of think of where that data started, where we appended it to, and where we're reading from it now. We originally had a data and we fed it into d3.py, right? And then d3.py returned pi data, and each one of those pi data elements had a data field, had a start angle, an end angle, and all those other things that it calculated. So it took each one of those elements and put it in a data field. Then that got passed into d3.arc, and d3.arc is drawing this, right? Now we're labeling it. We're not looking at that original data that we passed into pi anymore. We're looking at the data element as it was appended to each one of those pi data, and there's a data field in there. And that's why we have to go, for each one of these Ds, each one of these, we have a data field, and inside that data field we have that OS. Does that make sense?
Can we see that in the console? Is that there?
Yes, you can see it here. So this array here is pi data, right? This array 5. This is what d3.py spit out. And each object has, I'm going to minimize this real quick, has a data field, an end angle, an index, right? So what it did is it extracted that first little bit, that first little element, and put it inside this object under the data field, and that has an OS and a share. So we pretty much cut up our original huge data array into small ones and appended it to a data field inside this object that then gets passed into d3.arc. Yes?
So is it called data because that's what our original variable was, or is it always data?
No, it's always data. And Alex, stop me if I say anything stupid. Yeah. It's unfortunate because we call everything data and D, and and it can get a little confusing. But that's a good point. We could have called the original data my data, right? But the data attribute is always called data because it's pretty much. And the nice thing here is that we're keeping everything in this data attribute, right? And then later with the accessor functions, we say which bit we want to create labels, to create the size of the wedge. So we always have access to that entire data object. Instead of just extracting what we want from the beginning, we carry it along from place to place, and then we can always say, hey, go back into my original data and grab that third field and now label it with that. So that's why it's there.
So this is applied only for pi layout, or?
No, all of them. And that's similar to when we were doing the rectangles, right? When we do the very basic examples, we associate every rectangle to a single number. So in my talk on Friday, we had those 4 numbers, 4 rectangles. Our data is 4, 7, 13. But the data element can have anything. It can have an entire book in each one, and then we want to go back and take just the title. The idea of the data is that it's holding an element, and inside an element you can have one number or you can have the universe. It doesn't really matter. So in this case, the data element, we're using it to grab the values to create a pie chart. But the idea of associating data to an element is the whole concept behind D3. It does get more exciting than pie charts. Okay. So this is actually just the screenshot of exactly what we were looking at here. You'll see that for each one of these objects, we have the data field, we have end angle, pad angle, start angle, and the actual value. And the path is what is generated by the arc function. Okay, we sat through the boring stuff. Now we're going to go into really exciting force-directed graph layouts. Before that, I want to talk a little bit about loading in data. And this is going to come up in homeworks. So far, we've given you a little data set with 4 examples, with 4 elements in it. And as you know, that's not how it works in the real world, right? You're loading this huge file in, you want to make a figure that has a lot more data than those 4, and you're not going to copy and paste that into your HTML or your JavaScript file, right? So you have to load that in, and for that, JavaScript, D3 has a whole bunch of loading functions, D3.csv, TSV, JSON, text, whatever. It will load it in for you. Now, as you can imagine, the process of loading in data is not instantaneous. So if you have this huge data set and you say d3.text, load my text file, and then make all these figures, you have 2 options. You wait for it to load, and then you make your figures, and you do whatever, or you let it run in the background. And that is the idea behind the difference of something that is asynchronous and something that's synchronous, right? Something that's synchronous means it's going to execute it in the order it finds it, and it's not going to go to the next step until it's finished with the one beforehand. So if you say d3.load or d3.tsv, whatever, a file, and the next one you just want to print something out to the console, you're going to wait till this whole thing happens before this happens. Or an asynchronous function calling, it starts this, but it jumps to the next one. It will only print this out when it's done with it. It will keep going regardless of the fact that this middle one isn't done. So we're going to look at a quick example, and I want to see what you guys tell me. What is the order that this is? Sorry, that's so small. It's going to show up on the screen. Okay, so we have a console.log hello. Then we have a d3 function.json that's going to read in this JSON file. And here we have, the syntax is you give it the file and you tell what to do with it. So we have a function error and data, and you guys are going to run into this in homework. Hopefully you've already run into this. No, homework 3, not homework 2. Inside this function, you're going to do a whole bunch of stuff with the data, and you're going to plot it out to the console when you're done plotting, and then once all that's done, you console.log world. Now, given what I just said, who thinks that the order in which things are going to print to the console is the one on the right? Hello, done plotting, world. Really? Not a single hand? Okay, 2 hands. Who thinks, I hope everyone else raises their hand, it's on the left. Really? People are not participating. People aren't sure. Well, the answer is that one. And that is because d3.json is asynchronous, right? So what happens is you print the first one, hello, then you start reading in mydata.json. It's not going to wait until it's done to keep going, because it knows that this can take a while, right? So it's going to go ahead and print this world, and when it's done with this, it'll print done plotting. This is very useful to not bog down the rendering of your beautiful website because you have some really big data file in the background that's loading to make this one little viz. Right? So it's doing that, in the meantime it's rendering everything else and creating, and when it's done, it'll actually, and then it'll keep doing these things while this is still running. Now, a key thing to point out here is that because it will keep running, you cannot do anything here that depends on that data. So when you're first starting off with D3, I may or may not have done this, is you load in d3.json and you create a global variable called mydata, and you say mydata equals data. Wow, that's a lot of data. We should really start calling these things other things. Well, the point is you have this global variable and you put it in, and then you say, okay, well that's done. Now I'm going to make my figures, I'm going to plot my donut charts and so forth. And then your console says, there's nothing in this data file. There's nothing. Go ahead.
Is there a wait? Some kind of a wait?
So the idea of it being asynchronous, if you wait though, then how do you really decide if you want to wait or don't want to wait? Because let's suppose after this you do other things that don't relate to the data, right?
But is there like an option to say, okay, wait for this to finish and then do this?
This would be terrible software engineering because you don't know how long it will take to load the data. So if you say wait, like usually what you do, but you implicitly want to wait by simply executing your ever processing code in the callback function itself.
Yeah.
So you don't like say wait for a time, but you say wait until it's completed by implicitly like doing the calls to your plotting only when this is done. And like a little bit of a comment here, the $ is not correct, it's left over from.
Oh, there it is, sorry.
Yeah.
From my other example.
So the $ should be there.
Yes.
In case you're wondering.
Thank you, that doesn't exist. But exactly what Alex just said, so my point being that you're going to do everything that needs to be done with this data inside this callback, right? That is the only guarantee that that data is going to exist in your workspace when you actually need to use it. And you may not want to write it all in there, right? So let's suppose you have d3.json, my data, and then you're doing all of your plotting and your really complicated stuff. You don't want to have to put all that and then close your curly brackets all the way down here. So what you do is you actually can create a function called createViz, for example. And that's a separate function down here, createViz. So you do d3.json, my data equals data, createViz. Everything that happens within the scope of d3.json is going to happen sequentially. But anything you put outside of the scope of this function is going to happen as soon as it gets to it, whether or not it's finished loading the data. Anyway, all that to say, to explain the one line in our lecture code that why we do things the way we do, but this is actually important when you start coding more complicated things and you start using bigger data sets. Okay, so now we know how to load in large data sets.
Is there an easy way to tell which functions are going to be asynchronous? Or is it just a function by function basis we have to memorize them?
All loading functions are asynchronous, when you write a function, it is by definition synchronous. It's going to happen in the way that you put it there. It's just that the way they encoded the loading, D3 dot any of the ones that load text they are. Is there any other rule other than?
Any IO.
Yeah.
Usually IO.
Because that's the thing that takes longer, right? Anything you want to input or output, because it doesn't know how big it is. So it could take longer. But for the most part, all of these functions that you're using with your data inside your code, they're all going to happen synchronously.
Okay.
Okay? Okay, so this is what we're going to be creating. This is a force-directed graph layout. Okay? So it's pretty straightforward. It's composed of nodes and edges. Right? And now there are a lot of things coming into play in the way that is rendering on our screen. Specifically, there are 3 separate what we call forces, and I'll go into what those are. We're going to show you how D3 lets you play with these forces so that you can make it look like this, or you can make it look a whole bunch of different ways. And all you're really feeding into it are these nodes and the lines that connect them. I had a static one in case that one got annoying. We're not going to Okay, so the first thing we're going to do is recreate this simulation. Now, when you guys go look for examples, because you want to do this at home, because it's so exciting, remember that this has changed so much. I had to study up on what the changes were, and when I gave my talk on Friday, I wasn't even as comfortable with it as I am now, because the latest version has changed it completely. So look for version 4 examples, and there aren't that many out there. But for the D3 force, for version 3, it changed a lot. So this is one of those things that really, it's almost like relearning it if you use the wrong version. Okay, so first we're going to start up a simulation, D3.4 simulation. This does nothing. It doesn't, if you give it no nodes, it's an empty node array, and there's no forces. So this is, you're pretty much just preparing the scene. You're adding forces to this, you're adding nodes, you're adding links. What are forces? So forces are pretty much functions that will affect and will be used to modify the position of your nodes and how fast they move. That's pretty much it, okay? We can think of them in 2 kind of categories, but as Alex and I were talking about earlier, it's almost like you can phrase both of them in both ways. But forces can be things like gravity or electric charges. We can imagine them as physical forces or equivalent to physical forces in the world. And it also can be geometric constraint, like stay within this bounding box, or gravitate towards this point. Although this is exactly the example we were talking about. I thought of that as geometric, he thought of that as physical. But the idea is you are constraining how your nodes move on the screen. And these are the forces that D3 lets you play with. Links, many-body, centering, collision, positioning. The first 3 are grayed out because those are the ones that you saw in that first example. And I'm going to show you the effect that they have by removing each one of them and showing you what it looks like. And then the other 2, I'll show you what they do as well. We don't have them in the pedagogical example that we're giving here. So before I go to each one, I want to show you, so what does that look like in D3 code? So here we have that empty simulation with no forces, no nodes. And we add forces by doing .force. And we have 2 arguments here. One is a tag, and I'll tell you what that is. And then this is the actual D3.force link, D3, this is the name of the D3 force. This is a name, and you can name it anything you want. Here we named it link, charge, and center because it's intuitive, and we're going to use that later to get that force back. So when you see these, you can call it my force 1, my force 2. It's a name of the force, and then the actual forcing. And I'll explain a little bit what this is when we get to the link force, which I believe is the first one. Yes. So what is the link force? We're going to take it out, so I'm going to take that same code that I showed you in the previous slide, I'm going to take out force link, and I'm going to show you what it looks like. So that's our same simulation without D3.force link.
Entropy.
Yeah. So pretty much just, you lose all the connection, the links between the nodes. You no longer tell it that I want the strength between the connection between these 2 to be X. So that's what it would look like. So as you can see, it's a pretty important force. So it pushes them together or apart according to this desired link distance. So you have positive values and negative values will push it either apart or together. I'm going to talk later about something called a charge force, which is similar. But I want to point out that this only affects pairs of nodes because there's a link for every pair of nodes. Remember that first, when you saw everything together, the gray lines? Every gray line only connects one node to the other. So that gray line is what specifies how strongly they're pulled together, or pushed apart. So as far as the syntax goes, this again returns back to the idea of the accessor, right? So before we were using .value to access the value of the data element. Here we're using .id to tell the force link what is the field within our data that has that number that we want to use to quantify this. So if the ID is specified, it actually sets the ID accessor to this function here. So in this case, it's the .id field. And then if it's not, and then it's the node index. So it's the position that it's at.
Do you mean that you're accessing from the data the value that specifies that desired distance of the link?
Sorry, I said distance, but as I'm saying out loud, it's not the distance, it's which two it's connecting.
Okay.
So if it were, so this is the default function. So when you give, this is the data point and this is the index, right? So if you don't tell it, oh, give me this one field, it's just going to connect it to whatever the index is, 0, 1, 2, 3, and it's going to go back into the nodes and say node 0, node 1, node 2. I'm going to show you real quick what I'm talking about with this. So this is what a nodes and links file look like. Sorry, I should show this a little, makes it a little bit more intuitive, right? So we have nodes have IDs. Every node is one of those circles, right, on our plot, and then we have links, and links connect to nodes, source and target. So in this case, we're using the actual names to specify which are the source and which are the target nodes. So we need to tell it that we're using the field called ID in the nodes. So you're pretty much linking how do nodes and links talk to each other. And the easiest way to truly understand the impact of things like this is when we go through, and when surely after this class you go back through the lecture notes to play around with it yourself, that you can actually play with what this does if you take this out and how it works and so forth. Okay? So anyway, so that's what that function ID is. Okay, so the next force we're going to look at is called force many-body, or what we call the charge force. So in this case, I've left the links, I've left the center force, which we haven't looked at yet, and I took out the charge force. And that's what that looks like. Zoom in.
Is many-body
close.
Is many-body a repulsion?
That's too much. Say that again?
It's a repulsion force?
So it's either repulsion or attraction, depending if it's a positive or negative value. Oh, I didn't make that bigger, sorry. So pretty much there is none, right? So there's a force that links them together, and they're all gravitating towards the center point, and that's it. There's no charge. So it applies to all the nodes, and it can be used to simulate either gravity if they're attracted to each other, or strength, if the strength is positive, they're attracted towards each other, or electrostatic charge if the strength is negative. And I believe the default is -30 if you don't set it. A lot of these things, when you don't set them, they have a default value so that you actually come up with something on your screen without having to set every attribute ever known to man. So this is, and you can find the defaults by looking at the documentation. But I believe this one is -30. And the last one from that example is D3.4 center. So here we left the link, we left the charge, we took out the center. Does anyone have an idea what's going to happen here? We do not have a force called force center. What's going to happen?
It's not going to be centered?
Thank you.
Is it going to create kind of like a donut, maybe?
No, actually, so everything else is the same, and this is what it does. It just doesn't force it to be in the center. Now, the center of what, right? So we specify the center. So the centering, it pretty much just takes all of your mean positions and translates them so that they're around the position xy. So when we gave it the center, we said we want our center to be the middle of our width and the middle of our height.
So it doesn't pull them towards that point?
No, it doesn't. It
Just
takes that
reposition.
whole operation and translates it so it's happening in the middle of, or it's happening around that point. It doesn't have to be the middle. The center is really wherever point you give it, okay? And in our code, we'll see how we specify that. And so that's kind of important to not let it wander off our screen. Then we have D3.force collide. So that's the next to last one that we don't have in our example, and that's what that looks like.
Cool.
Yeah, so it's what it does is it, instead of every node, it draws a circle around it, invisible circle, and it doesn't let those circles overlap. So think of it as like a bubble around each node. So you can do it if you want to spread it out, and then you might want to change your charge force so they're not all trying to get so close together, so you can play with that. But that's what the collision does. And the last one is so unexciting I didn't even create an example for it, which is pretty much, it forces it to the one direction or the other direction. So think of it as a broken up center force. Instead of you giving it x and a y, you can just say, hey, I want it to go towards this x position, or I want it to go towards this y position. Okay? Another cool feature that you can do is you can fix a given node. So, can you guys tell which node is fixed here? It's gonna, yes, this one. I pinned this one down. So, Alex made a good point when we were talking about this, which is, this is actually gonna probably come up when you're interacting with your data and you wanna show a specific thing. And so you're clicking on it, and you can interact with these graphs, right, by clicking and dragging, and you say, you know, I really want to show what happens around this one, and I want it to be at a certain place. Then you go back into your code and you say node x, node 5 dot fx equals this, and dot fy. So this is where you go into our nodes array, and you fix, you give a given node fx and fy property, and that's what it does.
So could you just fix one axis, and so then it can move along the other one, but it...
You could, but for you to fix an axis, you'd have to pick which nodes you want along that axis, right? So you could, if you, I mean, you say, okay, I want all my blue points to be here, and I want everything else to be around it. Yeah, you go into, there's no which ones are your blue ones, and you go in and you set those. And you can do that at the JSON stage, or you can do that inside your code once you've read it in.
So you can also fix multiple nodes to get a nice layout if you want.
Yes, you
Cool.
could fix multiple nodes, yes. This
Cool.
example's not very ambitious.
That's good for like visual reference for the user to have some consistency sometimes, like if some of the network changes, but some nodes are still
Exactly.
consistent.
If you're refreshing it with new data, for example, but you
Mhm.
want certain points to be
Right,
to
right.
state at a certain point, absolutely. Okay, so we've created the nodes, we've assigned all these forces to the simulation. Now we need to tell the simulation, these are our nodes. So, unsurprisingly, you just say simulation.nodes, and you give it the nodes in your graph. Graph.nodes, because when we import our data, we called it graph, and we'll see this in our actual running example. And on ticked. So remember how, I can't remember, like the homework if you guys have already done, there's done callbacks on click, on hover, on that kind of stuff. So it's pretty much very similar to the syntax of other things where you say when this element is, in this case clicked, or ticked, and I'll tell you what that is, do this, call this function. So tick is what D3 calls every time increment of the evolution of that graph, right? So it re-renders the nodes at every x time increment, and that's called a tick. So you say, okay, every time it re-renders it, I want it to call that function ticked, and we'll see that what that function has when we go through the code. So here, the node that we're putting in the graph.nodes is an object, and the simulation will give it a position for its x, y, and a velocity for its x and y. This is all the simulation's job to assign to your nodes. You just gave it the nodes, gave it the forces, and the simulation did the magic. Okay? Just like, and so this is where we come back to the idea of tagging our forces. So remember how we gave it a force link, but we didn't give it links yet, right? We say, here's our force link. So now that we've loaded in data, and we want to give it the links, you need to call that force back and say, hey, I want to give this force this input. Now, notice that we assign the nodes to the simulation. We are assigning the links to the force. That sounded very Star Wars. We're not giving the simulation the links. We gave it the nodes, and the links only come into play if we have a link force, which is why we're giving the links to the force. And so I just brought this up to remind you that this syntax is only the name. Otherwise, you couldn't really retrieve this function back from this force, back from the simulation. Okay? So each link, just like every node, so just like we were looking at here, that's what the links look like. Every link is an object that has a source, a target, and an index, because everything that's in an array has an index. So this, every entry in your links object has a source and a target and a value. Okay, so that's it for my slides. Let's see this in action. I'm going to start. Okay, so here is a snippet of the JSON file that we're going to be looking at. And it's pretty much all the characters in les miserables and how often they occur. Okay, so we're grouping them, and then there's values. So there's nodes, there's links. So these are all the things we talked about before, sources and targets. So this is the bit that we talked about asynchronous data and synchronous. So d3.json is an asynchronous method. So we use the force layout to calculate the positions, and then we update them in these ticks, which are these time increments. Okay, so here we're using v4. We have in our SVG, we have our width and our height attributes. We were going to be using them to determine what our center is. So here we start the simulation, like I showed you before. Right, so we have an empty simulation, and then we're going to add in these three forces: the link force, the charge force, and the center force. And here we're using our width and height attributes to tell what our x and y are. So here we're pretty much just giving it the center. We could give it anywhere.
Why are you adding the SVG attributes, or are you adding it? What's the plus before SVG the attribute?
It just makes it into a number, the SVG attribute. Right, Alex? Doesn't that plus me? Okay, so here's our d3.json, and we're loading in this file, and our callback function here could be make graph layout and have that defined elsewhere. Okay, so this is an anonymous function, but if these functions start growing, if the process of creating visualization starts getting really big, you're welcome to make that other function and then just put the name of that function right here. Okay, so here we're going to create links, so the actual SVG elements, they're going to be lines. The data is going to be all the link objects in our graph. So we append a line to each one of these data objects, each one of these, each one of the data elements. We make the width of the line proportional to the square root of the value, and value is this. Right, so we have thicker lines means that occurred more often, thinner lines mean we're using one of the fields in our data to set the visual property of that line. So again, this is another okay, then we're going to make our nodes. So we're going to make a group with all the nodes. They're going to be circle SVG elements. The data is the nodes part of the JSON file. We're appending circles. We're making them all radius 5. If you wanted, you could make the radius proportional to something. Let's suppose we had another attribute called age, where we had the age of each character. We wanted to make the circles bigger for older people and smaller for younger people. The attribute R would be function D return D.age. Okay? The idea really is that you can control the appearance of all these elements with your data, and any attribute of your data, and that can get really powerful or really confusing and cluttered, but that's something that you learn. So here, for example, we're having the fill of the circles be a function of the group. Notice how, I'm actually going to scroll down here. We have, these are not randomly assigned colors. We have as many colors as we have groups in our original data. There was a group attribute, sorry if I didn't point it out. Right, group 1, group 2, group 3. And we created the colors using a scale ordinal color here. Right? And so we're pretty much saying, okay, we'll go into that scale, and depending on what the group value is, color it differently. So this is similar to on start, on drag, on end, similar to our on tick or on click. So when something happens to this element, in this case when it's dragged, d3.drag is a whole nother functionality where when you drag an element, it will do something. And we specify what we want it to do when you start dragging, when you end dragging, and when you are dragging, I guess. There's a difference between the start, end, and the drag. I guess when it's done.
During the drag.
Yeah, or it updates the position as you're still dragging it, that's right. Okay, then we have a title to each one. Now notice that this title, did we label it? No, it's when you, the element, yes, that's what it is. If we inspect one of these,
There's a mouse over.
Yeah. Oh, when you mouse over, you saw it on the bottom too?
Yeah. No, on the screen.
Oh yeah, that's right, it just took a while. There you go. But it has an attribute title, see here? That also has, you obviously don't have to go into the inspect element every time you want to see the title. Yes?
Sorry, one stupid question. What's the difference between an attribute versus a field?
An object field versus an attribute?
I'm actually using them kind of interchangeably, but attributes, or these elements have, you don't say a field of your SVG element. Your rectangle has attributes and has styles, and that is a little bit more of a fuzzy distinction. The way we could think of the difference between style and attribute is style is the way it looks. So the style is the color, and attributes are properties like its position or things that don't necessarily have that much of an aesthetic signature. I say fields a lot because I'm thinking of this as an object, a data object, and data object has fields, but in that case, field and attribute are also used interchangeably. Okay, so here we actually call once you do these three actions. We set the title. So here's what we were talking about before. We gave the simulation the nodes, and we say whenever there is a time increment, call this ticked function, and then we supply the links to the actual link force. So that ticked function pretty much is going to update the x1, y1, x2, y2 position of the links. So it's pretty much just going to say, okay, so that those gray bars that connect the circles, now we're going to put them here, the source, and it's pretty much just updating it so that it follows the nodes around. And the same thing, it updates the position, cx and cy, of your actual circles. So notice that this is not something simulation does for you, right? Simulation will create all of the fields that you need, but you're still specifically saying, set my x1, set my y1, and so forth. Yes?
So is the simulation constantly running as long as the object is...
Well, once it settles, like when it gets to the center, when it stops, you see that, I don't know if you can kind of tell from, well, you can't, here it stopped, right? It's not running anymore. You need to
So
refresh
you're
it.
not calling the tick function
No,
anymore.
no, there's time. And I don't know if you can probably set, like, to loop or to keep going.
This is a damping factor when there is a delta between two iterations is very slow, very little, then it stops taking.
Yeah.
You can actually influence when the
And then these three functions will actually tell it what to do if we do something like this. So it restarts it in a, not restart, yeah, the simulation happens again, but obviously because you're only dragging one element.
That's cool.
It's really cool.
It's fun. And, oh, so that's actually what you were just asking. The layout uses a cooling factor that stops the iterating cycle, otherwise it would just keep going.
Another question, so you had the moving fixed, but as you started dragging, it started moving as well.
Say that again? Oh, I didn't have it fixed here.
Oh.
This I had to fix in that one example. I unfixed it for the lecture notes. Yeah. Otherwise, you're right. It would not move. And I would play with the fixed one, but it's just a GIF that I recorded for the layout to show you guys. Okay. So that is force layouts. The last kind of layout that we're going to look at is Alex's favorite kind of layout, which is maps. It's a joke. Alex does not like maps. We are going to be using maps in homework 3, but just because we have to.
I might want to qualify this. Maps are good for certain tasks, but they're overused.
They are overused, yes. And so, it's very easy for people to kind of, but you can create some cool maps and you can cheat so that maps aren't necessarily geographically. Mike does some really great stuff. On the last homework, you guys are going to see a really cool map. I'm not going to give away what it's for, where you're not actually drawing the states. You have a symbol for each state, and then that's color proportional to a certain data set. So it looks like the US in the shape, but every state is just a single SVG element. So there's other ways of making maps that are creative and don't necessarily, because I think one of the things with map is that it gives disproportionate amount of importance to states visually, just because they're bigger and someone decided that, certain states would have a greater extent than others, but maybe the data that we're showing, we don't want that state to have such visual real estate. We want another one to have, and so it ends up confining one of the most important visual encodings that we have, which is screen space. You're taking up all that space. World maps, right? There's all these projections we're going to look at. The idea of how some countries take up a disproportionate amount of space on your screen, just because that's the way we're showing it on the map. Okay, so map, D3, the maps are based on a data called GeoJSON format, or TopoJSON, and this is an example of what it looks like, okay? So it has a type field or attribute, it's called feature collection, and then it has an array of features. So every feature it can be anything. In this case, it's states, right? And so there's the type, it has an ID, it has properties like name, it can have a whole bunch of stuff that later we can go back and grab, and it has the geometry. Now the geometry is obviously what D3 is going to use to draw it out. So there's a type, so it can be a rectangle, it can be this, or it can be, actually a rectangle would be considered a polygon. And then it gives you the actual coordinates, and that's what we use to draw the path that makes that map.
The comment, the difference between GeoJSON and TopoJSON is that in GeoJSON you have every shape like as like one continuous blob, and if you say you have a border between two countries, in GeoJSON this border will be represented twice, like as part of every country that borders it. Like in TopoJSON, this is kind of an optimized file format where you like have a border between two countries represented only once. So handling TopoJSON on a raw level is a little bit harder. If you work with D3, it doesn't make a difference because D3 handles both equally well.
Okay. Now notice that these coordinates, they're not the same coordinates as our path coordinates. They're not moving your pen from point to point on the screen, right? Because obviously that relates to your screen size and all those things. So we need to convert these coordinates into path coordinates so that we can actually draw them on the screen. And that's what D3 GeoPath does. D3 GeoPath, which used to be D3.geo.path. So it's very easy to take any of these and find out what the version 3 was, is that there was a dot in the middle of where your capital letter here in the middle of the word is. So let's see how that actually works out. So I'm not going to go through the whole width and height. You have an SVG. So the first thing we want to do, or one of the things we need to do, is create a projection. Now I'm going to show you a little demo that has all the projections. There are 1,000 projections. There are projections that I've never seen before. And then there are the ones that people usually use. GeoAlbers USA is one of the more common ones to look at the US. So you're giving it a projection, you're translating it so you're centering it in the middle of your screen, and you're setting the scale. You're making zooming in or out. Okay? Then we're going to create the path generator. So D3.geoPath is equivalent in a sense to D3.line or D3.arc because it outputs the path coordinates of what you're going to be drawing on your screen, but it's actually taking these coordinates, these JSON coordinates as input, and it takes a projection. So you say, okay, so my path has this path generator and has this projection. Now here we're going to load in our data, D3.json. We're going to select all paths, so we're creating path elements. The data is the features. So remember I said features was an array of a whole bunch of objects of this type. So that's what our data, that's what we're giving it. We're not giving it this field here. We're giving it, I'm pointing to my screen as if you guys can see me pointing. Features. Enter pen, which you're all very familiar with by now. Make a path. The attribute D is path. Remember, this path here is this path here, right? So this has the instructions of where to move the pen. This has the coordinates. And it makes this beautiful map right here.
Alaska is really off scale.
The what?
Alaska is really off scale.
And this thing, no matter what projection you pick, something is going to be, and we're going to look at some really cool projections in a bit. So here we're talking about...
What do you mean by off scale?
It's just the area representation is horrendously off.
Maybe we're so used to seeing it that way.
Yeah, isn't Alaska a lot bigger than that compared to the other states?
Yeah, that's what I'm saying, yeah.
Yeah.
So we're going to see, and you know what, this is, I'm going to jump. So these are all the different projections right here. Well, I'm going to show you, but let's see the effect that these here have on our map. This is zoomed in a little more, right? So this is the projection that we just looked at. So if we go in here, did I give it a scale?
There we go. Yes.
That's the GeoMercator projection.
It's not that simple though. There will be a lecture on map projections, and so Mercator, I think this is just plain coordinates, right? No, this is Mercator. Mercator is the most terrible projection with respect to size. So here, Alaska is way bigger than it actually is. For now, just notice that there's different properties on the map that you can optimize for. It's either size or like angle or having straight lines. But now you cannot do everything correctly because essentially what you do is you unwrap a sphere onto like a flat surface, and so therefore there is going to be some distortion. Mercator is known to be over-representing parts that are in the like close to poles. So Alaska looks a lot bigger here than it actually is.
Let's look at that
So
one.
this is equal area, yeah. So this is kind of a faithful representation of the size.
Don't use this one for your homework. Oops.
Yeah, that one's good.
And there it is. Now this is really cool. And it will go on forever. There's some really funky ones towards the end. Oh, I think it's random, it's not alphabetical, I was wondering. Anyway, so that's the projections. Here's another example of a map where we're actually going to take that map and we're going to color, it's called a choropleth map. So we color each state by a given attribute. In this case, agricultural output. So here, we're not only drawing the SVGs, but we're going to associate each one of those features to a value, and we're going to set its fill to that value. So similar to how we set the node, the color of the nodes, to whatever group it was, now we're going to set the fill of this feature, this path, to the agricultural output. Now, well, first let me show what it looks like. That's what it looks like. So it's very similar to what we've done before. So we create so we have the path that is the geopath from that same data set. And the projection is still the same one we used before. We have a color scale. Sorry, this formatting is weird. I didn't realize I must have messed with it, this range here. We have a color scale. And you'll note, and here we're creating these buckets of color. So we're pretty much saying, okay, everything between 0 and 1 is one color, everything between 1 and 5, or whatever it is. It's not a linear scale. We're creating 1, 2, 3, 4, 5 buckets. So believe me when I say there's only 5 different colors in this map. So here we're using similar to d3.json, now we're d3.csv, and it's loading in a CSV file. We're setting the domain of our color scale from the minimum value that we can find in our data to the maximum value. Then we load in the JSON file that actually has the states, and we want to join the data from the productivity data with the actual states data. So we cycle through each one of those. We find the corresponding state. And we set the value of that state. So inside the features, we set the value to the data value of the productivity data set. We select all our paths. We associate the features to that path, we append them, and the fill now becomes d.properties.value. And apparently, if you have undefined values, then you can return white. And that's what that looks like. And then our last example is a map where we have circles on top of cities. So instead of coloring it, we added markers to it. So again, similar same projection, very exciting stuff. We create the path here, GeoPath. We create the SVG, we load in the US states, and then again we associate these features to each one of these path elements. We create an SVG for each one, we append path, and so forth. Now here we're going to load in the cities data like we did with the productivity data, and we create circles. So here we're not appending one to the other, right? Before we appended each feature, we gave it a value, and then we did the fill of that feature was that value. Here we've drawn out the paths of the states, and now on top of that we're superimposing circles, and the data is the data that's in this US city. Each one of them has a latitude and longitude. Now notice that, and this is something that tripped me up when I was doing homework for this class years and years ago, many years ago, is that if you say you want your CX to be d.1 and d.lat, it will not show up on your page, because that needs to be translated to position on your page, and that's what the projection does, right? It says, okay, well in this projection, this latitude and longitude I'm going to place right here. If you say that you want your CX to be d.lon, d.lat, or CY, CX to be lon and your CY to be lat, it's not going to show up and you're not going to know why. Remember, you need to take that and feed it into the projection, and that will output the position on the screen that that marker needs to go on. And then we make the radius. In this case, we're having the radius of our circles be a function of the population at that city. We make it all blue. You could make it also proportional to some other data attribute if we wanted to. And we set it to be semi-transparent, so 0.8. And that's it. You guys are ready to draw maps and make force layouts, and you're done with D3. Yes?
It'd be cool to represent the United States as a network.
Yep.
So like the connections could be whether or not they share a border, and then the size of the area of the node could be the population or something.
Yeah, absolutely. You can do all kinds of really cool visualizations. Yes?
So is there a reason why you're pulling your CSV inside your JSON callback?
Yes.
And what-
Actually, in the case of this one, they're independent. That's it. You wouldn't have to. But my guess off the top of my head is you want to, remember how I said it's going to keep doing it, right? So let's suppose it reads the CSV really quickly and doesn't read the JSON first. It's going to draw the circles and then draw the map on top.
Oh, I see.
So this is kind of just a way to enforce that you don't have to worry about what happens first.
Layering, basically.
Yes, you're layering it in the sense that do this and then do this, and make sure that that happens in that order. Yeah, so I think you guys have time for
Okay, any other questions?
Yeah.
I was wondering, what are some things that the force maps are used for usually?
The force layouts?
Yeah, the force.
Well, for graph visualizations mainly, for networks. But also you could do any kind of simulation with it. So it's kind of like a physics engine, if you think about it.
Yeah.
But yeah, the main use that you will see in examples are node link diagrams that are automatically laid out. There's of course other layout algorithms that you could implement, and you can of course also implement your own layout algorithm, but the force layout for smaller graphs is just like a very convenient one. Any other questions?
I wanted to show that, you know, the one we showed with the Obama. Were you at the were you in this? I wanted to show you for example for, we could have just gone the other way. This one.
Yeah.
This is a really cool.
But this is a design critique actually, so.
Okay, so never mind. So that example was one where you have force layout, but the size of the circles was proportional to how much money was invested, for example, right? And then that made it, and then he divided it up and did all kinds of cool things. So, you know, we started with this really basic, simple looking example, but you can make it look really cool, and they used it in the New York Times.
Okay. So this essentially concludes the tech introduction for this class. You now know the basics about D3. You don't know everything about D3, right? It's not the goal of this class to teach you everything about D3, but it's really more about visualization theory, how do we really design perceptually efficient visualizations and so on. So the rest of this class is going to be about visualization techniques. And the first part of the class was mainly like a quick starter course in technology to get you started to be able to build your own visualizations. And So you will have to look at examples online and work on your homeworks and so on. And the homeworks are also designed to teach you some of the things. So as you saw in homework 2, you got steps that took care of some of the more difficult parts. And as homeworks like progress, in the last homework, for example, you will also have to, like, the first couple of homeworks are more to get your technical skills up and running, and then in the latter homeworks there will also be some design components. So we'll give you, like, here's a problem, design a solution to that and implement it. And of course the project will be just that. So we will start talking about perception on Tuesday, but for the rest of this class I've prepared this design critique, a record year of auto equals. Do you want to help me with this? Okay, so let's quickly take a look at this chart. And so here, this is interactive. The paper is only part of the game. And look at those. Did anybody try that? Does it not load? Yeah, I checked it yesterday. It worked there.
Maybe you can look it up on Google and just check out the cached version.
Yeah.
There's also that green arrow right next to it. If you go back to all. You're in videos, that's probably.
Yeah, I'm looking for what it is, a YouTube video of the. This is pretty cool. It's uncommon, like uncommon that the New York Times is down like this. Yeah.
It's a good place to put a we're hiring at.
Yeah. Well, maybe if they hired some, like if they kept my class, it would still work, but well. Okay. This is a little tough because here the animation is important. But anyways, I'm just going to tell you what it does. Or it is really boring without the animation.
Well, you only have 10 minutes, so if you want, we could start like office hours early and.
Yeah, I think since this is broken, let's revisit this. If it's not broken anymore, we'll do this another time. And if it's still broken, I'll do something else. I'm sorry about this, but this is really boring in a completely static setting, and I checked it yesterday and it worked. So.
Bring this next class.
Yeah.
Okay.